So now, you know how to use in your GPU, well, you know how to use all the cores in your CPU. You know how to use all the cores in all the string multiprocessors in your GPU. The only thing that remains is how to use all the GPUs themselves. So now we're going to use all the GPUs on top of all the streaming processors, and so that starts to become very interesting, right? Because now we can really take the full load. So the starting observation is nodes nowadays have more than one GPU. In the good old days, not really, but now just look at the AWS node, we have 4. So again, we have 5,000 cores per node waiting to be explored. So of course, using a GPU fully is good, but using all of them is more fun. So by default, you have 4 GPUs available, but you use 1. So by default, somehow, somewhere, there's a selection process that says, okay, this GPU will be the one where we'll run everything. In the same way, there's something by default, you can check which device is selected by default. The same way, you can also change which device you will issue your comments to. So we have already that, right? You know this one, where you can check if the device is there or here. You can get a total number of devices with a tiny trigger offset after passing. Oh yes, sorry. That is the identifier of your current device on which you're. And that is the total number of devices. It's always the same confusing notation. When P get num something, when P get something num. When P get them threads, when P get them num, when P get them teams, when P get num, when P get them devices, when P get devices num. Always the same consistent approach. That's the but that I don't. Again, I can bring this up in the OpenMP language community because it's confusing. OpenMP get device none and it's supposed to return There's one typo. Yeah. It's meant to be that's 2.1.2, 2.3. It's OpenMP gets none devices returns the number of target devices, not the hosts. But the host device is a device. So when I ask for the total number of devices, I expect the host device to be included. But no, it's only the target devices. There's this subtlety there.
There was a question on that.
Yes.
Did you get that one already? It's could we use data construct instead? And this was a few minutes ago. What
data construct instead?
So Carl, did you get that question answered?
No, I
don't think so. You mean a data construct across the 2 for loops that we were doing? I guess that's the question.
I'm not sure. This is when I stepped out to.
I imagine that's the case. The question about in the double for loop, could you just use the data construct instead? But that doesn't imply any parallelism to the accelerator. It just moves the data there, and then that's it.
Yeah, it's the data construct would.
I'll just.
Yeah, no, I was trying to find of benefits of having it because the data construct, the target data construct allows us to leave data on the GPU, which can be useful. But in this case, since everything was doing one go anyway, we were just moving data once. So now it's not the here. The thing is, you can use multiple GPUs, but we don't have yet the one. Oh, actually, okay, one more suggestion to the OpenMP language community. Having a construct that will automatically do what the for does on a for loop, or what the distribute does across teams. Some people would do that across GPUs, where you have many iterations, and some part will automatically go to this GPU, some part to this GPU, some part to this GPU. We don't have it yet, as far as I know. Which means you have to say, okay, this part will be done on GPU 0. This part will be done on GPU 1. Even if on each GPU you can automatically parallelize everything, distribute, for, and so on. And that's how you can effectively have multiple GPUs working in parallel. When you start to have only 2 GPUs that we have on the nodes, you have 10,000 cores working in parallel. So that's starting to become very interesting with the amount of output you can get. That would be interesting. And to give you an idea, just before we go any further, I was attending a talk from NVIDIA a few weeks ago about large LLMs, large language models for ChatGPT and others. And they were saying that, I think it was a big hundred, that to pre-train the model, it would take one GPU 31 years. And we look at the GPUs we have, right? These GPUs are not low end of whatever, they are nice GPUs. So for that to take 31 years of computation, that gives you an idea of a ridiculous amount of computation we have. Which is also why you have AI and HPC being best friends. Because AI people come with this ludicrous amount of data to be processed, and they come to HPC people and say, hi, you have 1,000 computers available. So, well, it was I count, it's 22, so I'll really go quick in this one, but it's what happened with HPC at the start. 300 years ago, I'll be very quick on this. 300 years ago, scientists were analyzing the sky by looking at the stars and by. Then, as technology evolved, scientists said, okay, we're going to record the stars from here to here 24/7 in like 4 billion by 4 billion resolution, and we'll send that to a program that will process it somehow. And then they came to HPC and to HPC people who actually were physicists at the start, physicists to create the HPC. And they said, okay, basically, we need something able to process 1 gigabyte of data per second. That was a long time ago, right? We took some time to develop the tools and learning how to scale everything up. And when we came back and said, okay, cool, then we can do 1 gigabyte a second. By the time we came back, they said, okay, cool, but now we need 10 gigabytes a second. And it keeps going up and up and up. And I think recently there's been a new telescope built that generates 1 terabyte of data a second. I don't know if you imagine when it's like processing 1 terabyte of data per second. I can't even imagine this anymore. Now, to indicate on which device, coming back to the actual GPUs, to indicate on which device we would like to run a certain target construct, we just have to use the device pause. Simple as that. You will just use the device pause and pass the ID of the device you would like to run on, and that's you. Again, 1 word. That's all you need. Any question on that?
Can loop over different devices.
Can you loop over different devices?
Yeah.
Yeah. As soon as you know how many target devices you have, you can do a loop here, a big loop around that, and pass in your iterator here. So you can totally do this. But yes, it would be nice to have a big like distributed target or something. That'd be cool. But we don't have it. But yeah, you can definitely do that. And you may even want to do that, right?
No.
Time for you to have fun. Okay, let's try to do this one together. So find the identifier of the host device. So how did you do this one? Find the identifier of the host device.
Everybody's still on the way.
Sorry?
OpenMP get initial device.
Let's try to compile this one. -1 sounds good to me. Find the total number of devices, of host devices, I should say. Target devices. Online, any idea how we can find the total number of target devices?
It's a challenge online. Let's take it up.
Is it simply get num devices?
Yes.
Woo! Rose to the challenge. Show you guys up in the room, man.
Oh yes. Now how to find the identity? Well, let's first compile and check that it indeed shows us what we want, what we expect. There are 4 target devices. Yes, we have 4 GPUs, so that's good. Now, how do we find the identifier of the default device? It's really about finding the right function, because in this unit we've seen 5 or 6 functions, so it's really about to find the right one. This is going to be useful, finding the default device ID, because this is really what is going to tell us where our targets take us to. Does OMP get something? Since we're looking for the default device, OMP get, yes?
Is it get default device?
Yes. Okay, let's try to find that. And it's 0. Okay. I should have put random numbers in there. And now offload to the default target device. Okay, so how do we do that? How do we offload something to the default target device? It's the very, very first construct we've seen.
It's like the target device identifier.
So that will be useful for the 2 questions that come after. For this one, we don't even need to indicate which device, because we want to issue it to the default one.
Okay.
But you're totally right. This is exactly what we will need to do here, indeed. So that goes to device 0, and that goes to device 1. Exactly. Now we need to change the default device. So how do we do that? Well, getting the default device number, that we know. We just did it a few questions ago. Get default device. Okay, that's easy. And how do we change the default device?
It's OMP set default device and then the number.
Yes, so let's put 1, for example, because we know it was 0. So it used to be 0, and now we'll change it to 1. And it should also that it's 1. So that's exactly how you can then redirect your transfers to a specific GPU.
Mm-hmm.
Okay? Okay. Last one. I think, do we have any questions here? Again, I feel like we went through quite maybe quickly. So do we have any questions on anything we just said or did?
Is there any benefits of this regard in complementarity to CUDA, or like is there any kind of difference why one should use OpenMP rather than CUDA? Regards to
Sorry.
this?
Yeah, Henry, I'm sorry.
Can you repeat that, Henry? We couldn't make that out.
Yes, yes. It's I was wondering just with OpenMP and CUDA if there is like with regards to multi-GPU, is there any like benefit of just using OpenMP rather than CUDA? Or yes, I'm not
Any
sure.
benefit using OpenMP? You're asking if there's any benefit to using OpenMP over CUDA?
Yes, with regards to applying many GPUs.
As applied to GPUs.
So, if you are after, it depends on the starting point. If you are after absolute raw performance and you want to get the best performance possible, you have unlimited expertise in the house, you want to go for NVIDIA, you're playing on NVIDIA GPUs, you want to use CUDA because it will give you a more detailed control over very specific features. However, if you don't have the expertise, or if you are fine with having, I'm going to give random numbers here. If you're fine with having 90% of the maximum performance that you have gotten with CUDA, but using only 10% of the time, then OpenMP is the way to go. It's a compromise. OpenMP, if you don't know anything else, is a great way for you to get access to the majority of the performance available on a GPU. But if you are in a very performance critical environment and having NVIDIA engineers around you is no problem, then you want to go to CUDA.
Okay, thank you. Yes.
Because yeah, as soon as you deal with CUDA, you can go really to low level. And of course, they always have more features coming, which means you always have more optimization techniques to leverage.
And there's another question.
Sure.
If we have to transfer some data between two GPUs, we need to use system memory as an intermediate place? Or if we have to transfer data between two GPUs, do we need to use system memory as an intermediate place? Or is there a direct transfer method using something like NVLink?
Oh, so they already have the yes. In OpenMP, I don't. Now, outside OpenMP, in CUDA, for example, you will want to come to the workshop on Monday. Because this is exactly what I'm going to begin with the workshop on Monday afternoon with what we call GPU to GPU communications. So again, if the question was, no, I know about CUDA, but it's not just OpenMP. In OpenMP, as far as I know, I just do not know if there is GPU to GPU communications. You seem to know already that there is such a thing called GPU to GPU communication because you mentioned the NVIDIA link. So GPUs can communicate together. I will not run what I will say on Monday. I will just give a very short version. They can communicate to each other without going through the host, without going through this slow medium in between. If they have the right, if they're modern enough, let's say, and if the hardware underneath allows it. And if the hardware underneath allows it, we can even have GPUs on different nodes communicating to each other directly. But for that, come on Monday.
And I'm putting the links for registration. Just give me a moment.
You want to?
Okay.
We have a link. Okay. So the only aspect we miss to really do everything we want, at least because, again, remember the title of this workshop is an introduction to OpenMP4 GPUs. But you still have learned already how to use every single core, every single streaming multiprocessor, every single GPU on a node. That's a good starting point already. Then when you get deeper into GPU programming, there's a whole part about the actual hardware, about coalesced memory accesses, about actual algorithmic optimizations, about the memory banks, about whole aspect of GPU hardware, because you cannot optimize the program for given hardware if you don't understand how that hardware works. But that's outside the scope of today. Even asynchronous could be seen as quite advanced for introduction, but let's go for it. So by default, everything you run is synchronous. In other words, when you call your target construct, the execution on the host is paused until the target finishes and the data is brought back. Okay, there is no overlapping of anything. So you cannot proceed until it's finished. Yes, you can have the no wait clause that allows you to do just the opposite. You may have seen that if you've done OpenMP on CPUs already, and I mentioned it this morning. When you have a for loop and you use the for construct of OpenMP on that for loop, by default you have an implicit synchronization at the end of it, which you can remove by using the no wait clause, and that allows the thread, as soon as they have finished, they can go and proceed with whatever comes next. They don't have to wait for all the threads. It's the same thing here. With a target no wait, the host will not wait for the target to complete, or to return, I should say, before it resumes execution. Okay? Yes, that's exactly the part of work. That's cool. And now, you may have different targets that depend on each other. And now the trick is, since we're non-synchronous, when we were synchronous, it was fine because we were running the first target. Only when it was finished, where we started the second target, so there was no problem here. However, now we launched the first target, so it's going to be executed on GPU. Maybe it's being executed as we speak, but I'm launching the second target, which has a dependency on the first target being finished. So now I need to take care of this, and OpenMP covers this with the depend clause, which is what we use in task-based parallelism. Remember this morning I said that there is a lot more to see in OpenMP, and I mentioned first thing I mentioned, task-based parallelism. That is from there. And yes, of course, if a target that is run asynchronously has no depend clauses, then it means that it has no dependencies, so it can be executed straight away or later or anything. Okay. Now, dependencies can be explained expressed in two ways. Either you need to read from the variable, or three ways actually. Either you need to read from a variable, write to the variable, or both. Okay, in, out, in, out. Exactly the same thing as task-based parallelism. Spoiler alert is because behind the scenes, all that is turned into tasks. But anyway, let's take an example here. 3 targets, A, B, and C, both of which here rely on A, which is set in the first target. So they cannot go ahead, they cannot proceed without the first target being complete. So this is why we say that this one, the first target, has a dependency of A, an out dependency because it's going to write to this variable. And the two other have a dependency of an in dependency of A because they just need to read from it. That allows the OpenMP runtime to make sure that the 2 targets at the end don't get executed before the first one is finished, but it allows the 2 targets at the end to be run concurrently, and if possible, then simultaneously. Okay. So I was thinking, do you want a quick distinction between concurrently and simultaneously? No, you're good.
Yes.
Yeah, because that's a very subtle difference, right? So I get back to CPU talk for a second. That's exactly the same thing here. A thread is a list of instructions. When you design your program in, let's say, 2 threads, multi-threaded, multiple threads, so in this case, 2 threads, you allow your program to run instructions from that thread or from that thread without waiting for the other one to be finished. You know that if we have 1 thread here, you know that this instruction needs to be executed after this one, and this one after this one, and this one after this one. However, instructions here have no dependencies there. They are 2 different threads that we assume entirely independent for the sake of this explanation. This means that it's concurrent. if I have a single core and I can run only a single thread, I can work on one thread, and then if I have to wait because that instruction is, oh, load this file, and that takes 5 seconds, I can put this thread on pause, on hold, move to the other thread, and start working on that thread now. This is concurrency, okay? They are not happening at the same time. Not at the same time, really, but they can exist without being after each other. They can exist next to each other. Simultaneous is if we have 2 cores, for example, and each runs one thread. These 2 threads will be taking place at the same time. So it will really be at a single point in time. There will be 2 instructions, one from each thread, being executed really now. So that's the difference between concurrency and simultaneous parallelism. One, the latter, the simultaneity, is just simultaneity. You don't have simultaneity. Because something can be symphony or simultaneity. So in French, we have the distinction between the two.
Yeah.
And
no, you can have simultaneity and simultaneously.
Okay, so I was looking for the concept of simultaneity.
Yeah.
So something that can be done simultaneously.
Yeah.
Yeah. So the being able to run things simultaneously is a gift from hardware. But for that, it requires to have this room to do things at the same time, and that is the concurrency that your multi-threading programming generated by creating multi-threaded programs. You created multiple threads that now can be either put on hold to move between a thread to the next, i.e. that's what your operating system does 24/7, or you can put these threads on different cores and have them execute at the same time. And threads has the same meaning on CPU or GPU, because on GPU we have CUDA cores, which run threads. Same thing. Anyway, I always like these questions of, do you know the difference between the two? One of the biggest questions, one of the trickiest questions I ask my MSc students at times is, when we're learning, I won't do that on Monday, I'm not doing it, but something on Monday we are going to talk about a lot is MPI processes and processes and things like that. I say, okay, but do you know what a process is? And I just look at it. A process is an instance of a program. What is a thread? Because we talk about threaded programming and multi-threading. What's a thread? Oh, a list of instructions. Done. The sooner we get that clear, the sooner we can progress. Because I still went through the MSc the first 3 months without still knowing. And I was like, at some point, I need to know what these mean. So what's a process? And you can see online, it's very hard to get a clear answer, because really many people don't have this clear definition. And it's not open to discussion. It's not a philosophical perspective of what, no, process instance of a program. Anyway, I love this terminology. And in the OpenMP language comments and the MPI forum, we have people who are really good at terminology. Anyway, I'm going off topic here, definitely. So this is the Fortran version of the C version we have here. Same dependency here. 1, 2. Okay. Now, there's something called construct synchronization, which is, at the end of the day, all these target constructs, which can be executed one after the other properly because of the dependencies, you need to know when they finish, because even if they can be started at any point in time and the dependencies will be taken care of, at some point you may be interested in checking, okay, but are they done now? And you can do that with what I call construct synchronization, where by using a single, at the end of a single, it will wait for this to finish. So it gives you a way to directly wait for all the targets to be executed. And that's the Fortran version of it. Or you can go down the road of more explicit synchronization by saying, okay, pragma OMP task wait. Because remember, target no wait basically creates a task. That creates a task with a dependency on the first task. That creates a task with a dependency on the very first task. So all these are tasks that we need to wait to complete. And Pragma, when the task wait, does just that. It waits for all the tasks generated, whether explicitly using task-based parallelism, which we had in them, or implicitly using the wait to complete before we go any further. And here is the function version of this.
So what is the dependent in A first section?
Sorry?
Why do we have the dependency on? We're just defining the dependency, or we're creating and the first because it says depend in A on the first
A
From the first loop.
on the first loop.
Ah,
Why do we need that?
one more typo for the 2.1.4. That's great because all these typos somehow managed to get through the international summer school and everything. Well, things are living today. Cool. Why do we need that?
Yeah, well, no, it says depend on the other ones.
Oh, yeah, the typos.
So
That's the match.
so it's supposed to be that. Okay.
Yes, yes. It was an in, it was out here, became in, then it stayed in. But it was always an out.
Okay. So that's the out. And then
Because you're spitting out the output and then other
Yes.
things.
Right. Yes. And one table here. Explicit synchronization table configured. Cool. I propose you have fun with the exercise and I have fun fixing the tables. Okay, so what did you do for the first part when we need to upload the A equals 1, 2, 3?
Target no weights map from A depend at A.
Map target no wait map
From A and at A.
from A and then it said depend out A. That looks good to me. For the second one, where are we up to?
Same thing, but with B.
Okay. Third one, third one will be a bit different.
So
So when we start to mix things, let's just take it step by step. Variable A, let's go alphabetical order. We need to map it. Okay. So we need to have mapped something A. Do we need to send the value there to the GPU?
yes.
Yes.
So we have the 2. Do we need to bring the value back?
No.
So just 2. Then for a variable B, I will do all the maps and then all the dependent. Variable B, we need to have something like B. Do we need to send the value to the GPU?
Yeah.
Do we need to bring it back?
No.
Okay, so that's 2. And now we have C. Oh, yes, because we don't need to send it, but we need to bring it back. Okay, and now the dependent. We must have dependent A, dependent B, and dependent C somehow. For the A, do we write or read or both?
Just read.
So that's in for B
In
and for C.
out.
Okay. So we can do the same thing here, up and missing a curly bracket. Okay, so A, we just need the value, we don't break it back. For C, same thing. And for D, we just bring the value back. We read from A, we read from C, and we write to D. Make sense? Okay, now what am I missing? So we have all these targets properly chained, well, hopefully properly chained to each other. But if I run, well, let's run it. Yeah, something tells me there's something wrong somewhere. Why do you think it's that?
Need the task weight.
Yeah, exactly. Because what happens is the printfs are called before all these targets have time to complete. Okay, that still seems a bit weird to me. Just a tiny bit. So C and D, it's both C and D. Is this from here? Somehow is not happening. Let's check something. If I put that in there, is it what I'm going to see? I strongly think so. No. Oh, okay. Interesting. So no, it depends. I'm not missing a map somewhere. We have C, which we map to from. We just need to bring it back. And it's depend out. If I turn that into this, we just have 2D. Okay, just doesn't like it. So what is it we're doing wrong here? It would have been perfect to have it right the first time was the final exercise, would have been perfect. Would have been too easy, I guess. So, target map. Are we missing a clause somewhere? Let's check because it's very easy to. One of the clauses we can pay attention to. So these values are.
Yeah, right. I mean, you have the from, right?
Sorry?
You have a map from C, okay, that's fine.
Yeah, we have the map from C, the pen counts. Everything is no wait.
Any thoughts online?
What? Oh, is that message online?
No, looking at their thoughts online. Well, let's try that to see if we have something that somehow fails somewhere else. That's an easy way to check. Just put all that in a comment, so everything becomes synchronous again. So if it's not correct here, we know there's something wrong. Okay, this is correct. Cool. That means there's something wrong here. Could it be because the dependencies are not properly expressed? Out and B, we have out and C, A and D. Oh, I think I know.
To let them together.
Because I think it overwrites it.
Yeah.
You try that? Because that's normally how I write
yeah.
it. So usually split it up. But I've never tried splitting it up.
No. Oh, okay. So that's not this. Okay.
And
Could it be the opposite here? Normally, no.
I mean, maps you can definitely split it up. Right?
Ah, I did it wrong. Could you send it in between that?
You take away the no wait on the C.
The no wait on
task
the
wait,
C.
I put a task wait on the A and B. I'm just curious.
Sorry, which?
So I was going to say put a task wait between the A B set, and you can put a few in just to see when it makes set, right? So you can put a task wait also after the A and B statements. Keep the no wait.
Oh, you want me to drop that every time?
Yeah, there you go. So that's enough, right? Because you know the first two are completely independent.
But it's because there's no way there's a task that is not done.
Okay, so the difference, if you go back, the difference between B and C. So it's why is it that doing depends? Am I missing something?
How? Oh, don't worry, I'm missing it too. I don't know what I'm missing, but I'm missing it. A and B. So somehow these is there it depends on? Let me check this.
Yeah, except there.
Dependencies. No, it's dependent. I must say it on because the dependency that they seem to be well expressed. Let's try that. If there's a typo in there, and I'm going to tell me this doesn't exist. Okay, so yeah, definitely right clause. Well,
The only thing I can think of right now that comes to mind, I mean, I did grab the latest not the latest NVC, but NVC, the 23 should be enforcing depends. Like it should be doing something. It should be properly streaming.
So that works. Oh, no, wait, it's still here. This one is still here. That, yeah.
Right, so if you put in this, you'll see that the difference between, no, they're both at 239.
Yeah, it's funny because they really have the same value. Okay, I understand. But the difference,
maybe something is not being enforced.
yeah, I was slowly start leaning towards the idea that it's not out of the state because I really don't see what's wrong here. Even if I turn things into froms, to the value to be passed there, we need to have this from here, and we have this out and we have this in. Well, for the time being, because I don't want to hold you forever, we already.
I'm gonna have to leave soon as well because I got to go to a.
Yes, so don't worry. Well, if I find something wrong, I will of course send it to Anne, who will forward it to you. Don't worry with the solution. But for the time being, I think that it's not our doing. So
I'm gonna bring it.
let's go back there. Up quickly to finish.
Thank you very much.
So you've learned how to upload your computation to GPU, how to take care of the mapping, even if it can be tricky at times, how to handle multiple GPUs, how to run kernels, or how to edit multiple target constructs at the same time, and hopefully correctly. We need to double check that. And you're also in control of the data movement in the CPU. There is a lot more to be seen, and none of this was mentioned this morning. So this morning, when I said there's a lot more to see, that is a lot more to see that was not even part of the first list of there's a lot more to see. And there's still a lot more to see outside that list. So there's really, really a lot. And all these are really reverse offloading is from the GPU, you call some CPU code. Because here we see you later. Have a good weekend. Thank you.
Thank you, Pascal.
Yeah, because right now we're the host and we issue the GPU, but now we have a lot of research on people being, okay, I want to do everything by default on the GPU, and when I want to do something on the CPU, I will target, so I will offload to the CPU. They just reverse the whole thing. They want to live on the GPU.